nanohub.org.
Online simulation, and more for nanotechnology.
Dr. Atilla Cakmak, or Ozgur Cakmak. He's an assistant professor here in ESM at Penn State. And also another familiar face will be coming to us from Williamsville, New York. Actually, Rich Hill, who's at Erie Community College. And he'll be coming to you from the labs there, and he'll be giving you some demos later in the presentation. So thanks to Ozgur and Rich for taking the time for today's presentation and adding to our cache of training material. Without further ado, I'll turn it over to Ozgur.
Okay, so a little bit of a different edition. So it looks like in the main title, I forgot to add the ion implantation. So we'll start with the ion implantation and then go into oxidation. And the last one will be atomic layer deposition, or what's called ALD. And then Rich from ECC will give us a good demonstration over there. Okay, let's start with the ion implantation first. What do we mean by ion implantation? Or first, why do we need an ion implantation initially? So if this is our layer that we've been seeing so far, this is the fourth of the deposition series, right? So you guys have seen that we could grow materials, or we could have some like substrate initially. What we would like to do is, for example, in this kind of a very commonly used silicon material, we might want to make it a little bit more conductive than usual. Originally, like if you don't do anything on the silicon, then it's going to be intrinsic material. What it means is like the silicon and silicon, all those silicon covalent bonds will be there. There won't be any additional electrons to flow the electron through. So for example, let's look at another semiconductor here instead of this common silicon, but germanium. So in the normal case, germanium has these 4 electrons like you guys can see, and it's sharing its 4 electrons with its neighbors, doing the covalent bonds. Then we have, let's say, if we have an infiltration into this crystal, into this atomic orientation, and if we start to have, like, say, boron in the crystal, boron will only have 3 electrons, so there is going to be an absence of an electron, a vacancy here. That's what we will be calling a hole. If we dope it with, that's the key word, dopant, dope it with, not with boron, but with phosphorus, then we will have an additional electron, because that's what phosphorus will be able to offer, right, in its valence electrons. So there's going to be an additional electron that's not going to be shared here, so that's going to increase the conductivity, because this electron will be like much more free to move around the crystal. When I mean crystal is like these atoms, cascaded atoms, germanium atoms here. So this is also going to increase the conductivity, will make it much more conductive, this material, because now I have this absence of the electron here. Any electron will have a chance to go and invade this vacancy, and there we go. If we call the conductivity as electrons hopping from one location to the other, then we just establish what we're looking for. The electron has moved from one side to the other side, and then we have the conductivity in action. Great. In order to do this, we will need to introduce these dopants into the material. Like you can see here, some areas are masked here, so we don't want infiltration in here, but like we can introduce the dopants from the top, like it was done in the past. So this is more of a historical way of doing it, and that's what we call a diffusion method. So I have a small interactive tool for you to see, so we can understand diffusion much better. But this is like I was saying in the old days. So this is from this website here. So you guys can see that how this diffusion, how this infiltration is happening. So we have materials that are the dopants that are introduced, okay? So this could be, again, boron or phosphorus. And then the diffusion is taking place because we have like an elevated temperature. What is happening in the elevated temperature, the diffusion is much more likelier, and then we have the diffusion of the material from the higher concentration to the lower concentration, right, into the depths of the material, replacing the sides. So if we like to get a concentration information, so this is the distance information, what distance? So this is the distance into the this bulk material here. Okay, so that's the distance in here. So let's say we have like have a chance to get a concentration distribution analysis by taking a cross section into the depth. So like from here, I'm just taking a cross section. Okay. So there are two phases of this. First, I do the deposition of the dopant, the material. Then I will do the deriving by employing the temperature, and then we will be able to diffuse the material, diffuse the dopant more into the depths. So in the first case, the deposition will take our dopant concentration into the depths, like you can see here. We start with a high concentration, so this is concentration, 10 to the 21 per centimeter cube. So these are like the general concentration scales that we have. And then into the depths of the material, we have like a decaying concentration, like you can see. Let's say, just to show you how the temperature will be affecting what we're doing here, if we have the temperature to be much lower, of course, you can see that that tail will be dropping, because the diffusion process, even in the deposition process, while we're introducing the dopant, will not be able to efficiently go into the depths of the material. So 836 is definitely going to drop down the concentration into the material. And if we make it higher, of course, so we will be able to drive in more. I mean, when I say drive in, deposit more, the actual drive in will take place in the second phase, where we will introduce the higher temperature, like you can see, like 1000 degrees and more. And in this case, we let the diffusion take place and get our dopants that we already introduced into the crystal to diffuse more into the crystal. Like you can see here, where like we have a more like longer tail diffusing into the crystal. So that means I have more infiltration of the dopant. Of course, temperature is not the only parameter. You can play with this in your classes with the students, and then you can like say, I'm going to change the drive-in time. So instead of a 41 minute, I'm going to make it longer. So if I make it longer, of course, apply the heat for a lengthier amount of time, then the concentration will infiltrate more. So you see, we now already reached like 1.6 microns of the material. If I make it for a very quick amount of time, like a burst, then that will only reach this much, right? So that shows us, all these calculations can easily show us like what we can do or what we can't do. In any diffusion process, we have to be very careful, because it's very temperature limited and dominant dependent, but also like when we think about the things that can go wrong, we have not a great control of what's happening here, if you think about it. So like the diffusion might really take it into the mask, like in these size, or we might not be able to see like where this is going to go. It's a bit out of our control. We have to be really on our toes. Much better way of doing this is with implantation, and that's what we're really going to talk about today. So, and what's being done mainly in industry is the ion implantation. Instead of the good old diffusion net technologies, we have the ion implantation. So we're going to increase the speed of these ions, and then we're going to like mask some areas. We're going to say, okay, I want this area to be highly conductive. And then we're going to infiltrate that area with highly energetic ions. So we're going to bombard that place with ions. What's going to happen? We're going to damage the crystal, and you see the damage that we're doing. Then we're going to repair the crystal later on. Okay, so there's all these like advantages versus disadvantages comparing the two techniques. What were they? The ion implantation with the high energetic ions, and the other one is the diffusion method. So as the advantage, it's very fast. You don't have to wait for 41 minutes like you saw with the diffusion process. It's a low temperature process, so apparently we don't need to facilitate the temperature, right? So we have like a wide selection of masking materials because it's a low temperature material process. Like, for example, if you think about photoresist, a polymer cannot withstand like 1000 Celsius degrees that we just seen in the diffusion process. Forget about that. The polymer will decay, and then your furnace will also be like very much contaminated. yeah, you can achieve more complex profiles. Like you can say, okay, I want this area to be like fine-tuned to this conductivity, this area to be less conductive, etc. As for the disadvantage, that's going to be the thing that we're going to highlight. That's why we can't immediately show you a demo of this tool, because it's a very, very expensive tool. It's more than $1 million easily. Like only like companies, and I have a friend here at our material research lab who actually run these ion implants for IBM for many years. He says, like, I had like 6 ion implants under my hand. And I can believe that, because IBM can afford doing that, but not like a research university at Penn State is not very much interested, because we can't really allocate that much of money into this tool. We need to have really good applications. We're not building transistors, and most of the founders, semiconductor founders, are really interested in these kind of expensive tools. But it's really the way to introduce the dopants in a much more professional way rather than the diffusion. But having said that, in our more naive research environment, we're still doing the other methods like diffusion that I just shown you, or spin coating methods that also can introduce the dopants as well, that we're not going to touch today. But we also have like these damages that's taking place into the lattice, right? So we have to also think about how we need to repair the damage. All that needs to be taken into consideration. So like I was saying, ion implantation is the way to go after 1970s. It took over the old technique diffusion. We used ion implantation to, well, these are other fancier ways of saying it, but saying we allocate like where I'm going to have like highly conductive areas, or where I'm going to have like a certain conductivity, where I'm going to have like a less conductivity. I can fine tune that very well with ion implantation. So we're going to bombard the material with, say, ions like boron, arsenic, and we know that these are going to be the regular dopants, and when we introduce them into the crystal, they will like create vacancies or holes, like I shown you, or extra electrons, and then increase the conductivity accordingly. Okay, so now we're seeing here an ion implanter schematic, a very simple schematic from the top view. What it entails is first the ion source, so we need to create the ions, right, obviously. Creation of the ions will be made with the help of these quite harmful gas, like arsine, for example, phosphine, all those, they're very harmful. We're gonna break that into an ion and then create arsenic ion out of this, okay? We're gonna charge that with the voltage supply and then ionize that gas. And then once we have the ion created, we need to select the right ion. For example, if we like to create boron, we need to like say all that from that diborane that can create all many variations like I will show you. There's going to be a mass spectrometer here that's going to basically select the correct ion that we would like to work with. And I will show you more about this, what we mean by that. Then we will accelerate these ions. Okay, the mass spectrometer here is actually here. I just was tricked by this aperture here. It's actually here. So we will get the ions. So let's think about this as the ion source here. And then we'll get the ions, apply the magnets together with the, this could be our mass spectrometer. We'll get our correct ion, let's say the boron ion out of this, and not touch the other choices. I'm emphasizing this because we're going to see we have a lot of choices that we can create. Not just the boron can be the output, but many others can be also the output. Now we have our boron ready, but as I said, this needs to be energized. So this needs to be really a highly energetic ion. So we need to have an accelerator. This is where we're going to like increase the speed of the ion before the bombardment, and then we will scan on the surface here, not just like one tiny location, right? We will create our like kind of an ion beam, and then we will be able to infiltrate into the correct areas that I want. So we need to have some electromagnetic scanners. So these are the scan plates to be able to deflect the ions and to get the ions in correct location. In all this mess, we can have like byproducts coming in. Yeah, so this mass spectrometer is here to actually filter out those byproducts. But what if we still have like, say, neutral particles? We have like these neutral traps for them. What happens, let's say, if I have like, say, for example, arsenic is coming in, but for some reason, I might have arsenic in here too. the arsenic ion as a charged particle will be able to, will be able to get this kind of a curve, right? This sharp curve, because this is a charged particle, and under the effect of the external voltage supplies, electrostatically, if you want to think about it, that we can give it that kind of a bend. But this arsenic neutral particle will not be able to do that, so we can have other means of filtering those out too. So this is a more realistic thing of what's going on. We start with the ion source, like I was saying. We have the mass spectrometer, and then mass separator magnet. You can think of it that way as well. I will show you what we mean again, and then we will accelerate it, and then get like these kind of curves, so that we will filter out the particles that we don't want, and then we will ionize, we will bombard the surface. Okay, like I was saying, we might have like started with a gas, and to get in the end, so arsenic, boron, whatever, and boron is what we really want. Say boron is here, so I just want to get this, for example, okay? But we may have other byproducts like fluorine, for example, fluorine ion too. I don't want that. Or some other ions as a decomposition of the gas when we charge and ionize the gas. So what's going to happen? The good thing is, when we look at the whole spectrum, their atomic mass, in terms of their atomic mass, they are going to be located in different locations. We know that we might have a chance to predict where these ions will go. Say, for example, the heavier ion will take a larger trajectory here. And how do I know that? Well, I know that this will be under an influence of a magnet, an external magnet, okay? That's why it's bending like this. And for those more interested, we have like these Lorentzian forces acting on these ions, but we can just think of them like some forces, electromagnetic forces, and these charged particles will be bending accordingly. But I know that depending on the mass, the m here, their velocity and their radius, there's radius here. So if we take this radius up here, like you guys can see, right? So this r is going up here, so it's in the bottom, called denominator. I forgot the English word. Anyway, so it's at the bottom. So we'll take it up here. So you can see that m is related to the radius. What radius? That radius, that's the this radius here, the trajectory, the radius of curvature. So if it is a heavier ion, of course, its radius will be larger, so it's going to go there. But if it's a selected ion that we want, then great. Then we can predict its trajectory, and then we can get that ion out of the system to bombard the surface with a shorter r. So we can really fine tune to what we really want and just get the one that we really desire, and then filter out the others. Okay, so what's going on when we send the ion into the surface? So let's say this is our ion. There are two main mechanisms that are happening. First, the electronic stopping, where the ion is very fast, and then the ion is only like in interaction with the electron cloud. It's, of course, losing its speed, but due to this interaction, and that's creating the heat, of course. But that's it. So the ion is in interaction with the electronic cloud, and then that's how it dissipates its energy. The second way is nuclear stopping. So we have the ion just head collision into the atom itself. Okay, so then that's the other way of stopping the ion, and obviously, right? That's the second mechanism. And depending on the weight of the incoming ion, hydrogen, boron, arsenic, all these mechanisms will be occurring differently. So let's look at this. So let's send two ions at the same speed, okay, same V. So what does that mean? So, or say not the same V, let's scratch that, same energy. So E and E, so this is, let's say, phosphorus, and this is, let's say, boron, okay? I know that phosphorus has higher mass, so its mass is larger. So let's make it a little big. Let's make it a little bigger than the other one, boron. Okay. So what will then create? So we know that the energy we can like in the non-relativistic case, of course, but we can say that energy is 1 over mv squared, right? So if the mass is larger, its speed is smaller, right? We all agree about that. So that means that for the same energy of these different ions, say the phosphorus here and the boron here, the boron will be much quicker. That means the boron will be like super quick, and it will not have a great amount of time to interact with the silicon atom here. So it will just be like an interaction with the electronic cloud, and that's it. That's how it's like mainly being stopped. But this is not a great way of stopping, right? So it will infiltrate a lot more, obviously. How about boron? Well, boron will be slower. Slower means then under the influence of this nuclear stopping, there might be more interaction time and more collusion. So there will be then, this will be much more efficient collusions taking place. So boron will be stopped much earlier. I hope that makes sense. So if you think about it, then arsenic will be the heaviest one, so it will be stopped a lot earlier. See, arsenic is here, it's just stopped like here very quickly, whereas boron, with the same energy, it will be much quicker and then infiltrate a lot more into the depths of the material. So this is what's going on. We have the crystal damage, like we were saying. We're sending arsenic, and then it's just going into the crystal, just dislocating the silicon atoms, and creating the vacancy sites here. And these silicon atoms, the interstitial, they're not in their exact location. So we're damaging the crystal, but also locating the arsenic somewhere. What arsenic is doing all of these collusions because it's going through nuclear stopping, because there's too much of time of interaction there. So it's able to knock off the particles, but it's also in a lot of interaction with the atoms themselves too. So now these are like calculated numerically with Monte Carlo type of calculations. So we send the ion in here. So we've done this like in the previous two discussions. We'll revisit that. I uploaded the location, the website again. We're going to use SRIM one more time. So we send the ion from here, and it like a lot of ions. Of course, we like to predict where it will be heading, where it's going to be located. And when you do the calculations, it's very interesting, but even if you don't do like these kind of detailed calculations of like trying to predict where it might go by luck, and if you have to do that, we have to calculate like thousands of ions at the same time. You can basically analytically express it. When I mean analytically, so this might look for some of the students quite dreadful, right? But we can just think of it that way. Like say the students, okay, think about your grades at the end of the semester, right? So there will be like some high grades, low grades, whatever. So the ions will also be like that. Distribution will be like that. So Gaussian distribution, a bell curve, right? So a lot of the ions will be implanted in here. That's going to be the mean, and then there will be some variation, of course, like the population will be less and less if we go to the other both sides. Of course, it's not going to be a symmetrical Gaussian, having said that, but still it's going to mimic a Gaussian, and we're going to look into that. Maybe we can look at it very quickly. So this is again, reminding you, this is the software from before. Okay, so when you click it, it's going to bring in here. So first thing you can do is this first part, that's going to ask you like what ion are you working with, say boron, and you can give the energy, okay, from the lower energy side to the high energy side. I don't know if you can read it well, but this is like 10 electron volts to or 10 kilo electron volt to 10,000 kilo electron volts. So in here, and then we can do that into silicon, a very simplistic way of thinking, just into the most commonly used material, of course. And then I just hit the, okay. And then it's gonna give me like two main important things. So this is the projected range and the straggles on the 2-dimension, of course, but two important items in if you would like to simplify this, the range and the straggle. So what it means is for the energy, different energies that I'm infiltrating into, the range where these ions will go, the bell curve, where they will be heavily found, will change, like 437 or angstrom. So that means they infiltrated like 43 nanometers into the depth of the silicon. So if I increase the energy, look what's happening. It's increasing accordingly. So like say if I increase it up to 450 kilo electron volts, really high energy, it's relativistic right now. I think it's going to really implant very much into the depth. So it's going to be like 1 micron already. So that's as far as we go. And we can go in even deeper with the increasing energy. And then there will be also the deviation, of course. So that's, you can think of straggle in that sense as well. So after having looked into that, that's not the only thing that this can do, if I'd like to remind you. So you can also click on the other one, the trim calculation, and we can do the same thing in here, boron going into silicon with a smaller, like 50 kilo electron volts, okay? We're gonna do it for 1,000 ions quickly, or maybe even 100. Okay, and just say calculate, and then this is happening here. So you see the Monte Carlo simulation that I was referring to, it just calculated. It was very quick because it's just calculated for 100 ions. Let's look at the ion distribution here. Yeah, so you see it's gonna become like a Gaussian. So if you do it for a much more amount of like ions infiltrating, it's gonna look more closer to the Gaussian distribution, the bell curve. So what we're looking is like a snapshot again into the target depth. So the most amount of ions are located in here, and that's the ion range showing us where they're located, kinda. That's going to be like the analytical way of Gaussian way of understanding things. That says like 170 nanometers, that's where they are. And then the straggle will give us a rough idea like about these variations on the both sides. And you can also do cool things with your students, activate this 3D plot and look at the like where they are in the 3D, but it looks really not great because we didn't wait long. This was just for 100 ions. If you do it for 1,000, it will be even better, of course. So one needs to really be very cautious about a couple of things. For example, let's say you have your mask here that you'd like to mask this area here because you don't want ions to reach here. But think about it. So most of the ion population will be here. That's the range that we were talking about, the projected depth. And then you will have like this kind of a tail that will be determined by straggle, but you don't want the ions really reach here. Then you have to think about the thickness of your mask. If your mask will have enough thickness to prevent that from happening, right? So for example, in this case, it's a photoresist shown with PR. Will that be good enough of a thickness? Then let's say, look at this plot, boron, phosphorus, arsenic. We know that arsenic is the heaviest. So at a certain energy, let's look at it, arsenic infiltrates, the projected range is the lowest for the arsenic. And this is like showing us like a very quick estimation of like what should be the thickness of your mask. That's going to be about the projected range and also about the straggle. So another thing that can go wrong kinda is the following. So you send your ion, but the ion can just miss all these collisions and can just go through the whole crystal structure that we will call channeling effect. And this can really happen because look at the silicon, for example, from this perspective, from the top view in a three-dimensional, more realistic way. If you, by some chance, send it at the normal incidence, and if it just goes through the crystal, there's nothing really going to stop the ion, right? So that will introduce a lot of ion distribution into the depth. So this is with the channeling effect. This is without the channeling effect. So that's a terrible news for you because you have made this area to be a lot more conductive than what you really wanted. So in order to circumvent this, people have come up with these really good ideas. Like they said, what if I give it a little bit of an angle, like 7 degrees both ways, plus minus 7 degrees. Then I can, up to some degree, prevent this. How? Let's look at this crystal one more time. If I'm coming here with the 0 degree, like, I mean, at 90 degree in normal incidence, then that means I'm just have the luck to go through this channel. But if I come with a little bit of a tilted angle, then that's a really like an optimized angle. Then I can maybe just see one of those silicon atoms, and then there won't be much of a channeling. So this is heavily done. Now let's start talking about the crystal damage that we're giving into our crystal. We're knocking off these particles, and then we're creating these self-interstitial layers, and also creating vacancies where we used to have atoms. Now we have vacancies, the silicon atoms. And we're really doing it a lot of these damages, mainly when the the ion has lost its speed, right? So when it's closer to stopping, then that's when we have the damage, and that's what we call the end of range damage, EOR. So you can easily see that with this kind of a transmission electron microscope image that we have in here. That kind of a damage is shown here when the ions are about to stop, so we will have that damage. But then, having said that, this damage might be a great way for you to engineer your system against the channeling effect. What do I mean? Let's look at the channeling one more time. So we had a luck to go through these channels, like I was saying. You really can, if you have like this kind of a very periodic crystal structure, if you just like send your ion and it happens to go through the channel, you will find your ion at the other side. But what if you intentionally create an amorphous material here? Amorphous meaning not a crystal structure again, but like a damaged structure. So instead of a crystal orientation with perfect periodicity here, if you send too many charged ions and then higher dose, that's what we mean. And if they just like collide with these the silicon atoms here, we can make it an amorphous silicon intentionally. Why? Because we don't want the channeling to happen. So that's a way to battle against channeling. So we have, like in this case, an engineering of the damages in order to circumvent the channeling altogether. So you're seeing here the curves for the critical dose corresponding for the temperature, the critical dose that you will require for creating the amorphous layer here. So you can see here that since boron is the lightest all of this, so it will not be able to do much of those collisions. So it will require a lot more higher dose than phosphorus and the other one here that we're seeing. So we really need for the boron to do this same kind of amorphization, we need a higher dose, a lot more of the boron going in there. That's what it's all about. Then after that, you can repair your crystal by, thankfully, due to, again, diffusion. But this is going to be done with a very rapidly increasing the temperature in a very quick sense. So if once we have the damaged crystal, we can repair that by increasing the temperature very quickly and getting the atoms in their location. So these tools are called rapid thermal annealing tools, RTA. So it looks like that. We have, and you can see the ramping time, the heating rate, 200 Celsius per second. So that's a lot. As you can see. So these are going to take really like minutes at most. So these are going to be using like these kind of rapid heating sources that can come from rapid power, lasers, electron beams, high density halogen lamps, all those. And you can have these as desktop items or like more complicated tools to repair your crystal. Now, I shared a lab, and virtual lab that I do with my students here. I'll just walk you through that very quickly. What I wanted the students to do is to use both the analytical expression using the Gaussian, and you will see it in the supplementary I already uploaded, and I guide you every way in all steps. So they calculated analytically with the Gaussian approximation, like you can see here, and they tried to find the same kind of distribution by using SRIM, as you can see, depending on, say, the dose. This is corresponding to dose. This is the straggle we were talking about, and this is the range. So that's it. You have everything. So once you have those items in here, you can express that analytically, and you can compare that with your SRIM result. They're really going to be quite similar to each other. Now let's look at the final results. So we have here boron, and this is kind of like the analytical expression to what it's corresponding to, and this is what's showing us we have infiltrated with the SRIM, the Monte Carlo simulations, and that's what's going on. Look, they're kind of similar. But if we say switch from 50 kiloelectron volts to 300 kiloelectron volts, then we infiltrate into the silicon a lot deeper, right? So this is into the depths of the silicon here in terms of angstrom. So look, we have infiltrated into the 800 nanometers of the silicon here just by increasing the energy of the incoming ion. Now we're using phosphorus here. With the 50 kiloelectron volt phosphorus, we weren't able to penetrate much. Why? Look at the boron, just comparing these two. We just stopped a lot earlier. Why? Because the phosphorus ions are much heavier, so there's a lot going on, a lot of collisions, right? So they stop a lot earlier. Again, increasing the energy will infiltrate them a lot more. All right, so that's one of the labs. The second lab that I uploaded, the virtual lab that I uploaded, is about implantation and diffusion. So first, in this case, the student does implantation and finds this nice Gaussian distribution curve. And by the way, this is our mask here, the silicon dioxide here, okay? And underneath that, we have silicon. This is the red one is silicon. So we're looking at from the, like, if we look at from this view, it's corresponding to like looking at from this view. So you see, this is our mask here, just like toggled or flipped here. And we have the highest concentration corresponding to this point in here. After that, after the ion implantation, just to repair the crystal, like I was saying, we have to rapid like anneal that, rapid thermal annealing. So the diffusion will take place and the concentration will be changing. Let's do that together. By the way, I'm designating these MATLAB codes here, so you can go back, and if you're familiar with MATLAB, use my code or just modify it in any way you like. So let's look at that quickly, and I'll show you what I mean. Okay, so this is what the MATLAB user interface would generally look like. And the code that I uploaded for you is here, ion RTP. So we're going to dope a dose of 10 to the 11, doesn't matter for us, per centimeter square, some ion, but just illustratively, this gives us, the students, an idea, like saying when you run this code, it's going to say like for how long this rapid terminal annealing will take place. Let's make it just for 1 minute, like 60 seconds, right? All right, so when I do that, the first curve that will bring will be the after the ion implantation. So this is right after the ion implantation. We have the ions heavily found in here in this location. Now, if I click on this curve, this is going to show me what will happen if I rapid thermal anneal it like for a minute. So you see, diffusion is taking place from the highest concentration to the lowest. So we're kind of like getting the ions a little bit into the depths by rapidly thermal annealing, increasing the temperature by both to repair the crystal, but also kind of like smooth out the distribution too. So, but if we have not a good mask, so this can also happen. Let's go to another case. So let's say now, not for a minute, but 10 minutes or even more, 100 minutes. So something went wrong, so the user just left it in there, let's say, in the rapid thermal annealing tool. Oops, let's run it again. Okay, so this is the same thing right after the ion implantation. Look at the distribution, 3 times 10 to the 15 per centimeter cube. That's the concentration of the ions in here. And this is what's going on after the after leaving in there for, what did we say, 100 minutes. So that's crazy. This is a very long time, and that looks like the tail. The tail says, I really infiltrated a lot into the depths of the material. So that's not great news for you, because your mask does not serve your purpose anymore. So your mask here will not stop the material, so it will infiltrate into silicon. Right, so that concludes the ion implantation part. Now let's try to find another way to make things less conductive. So we found a way to do more conductive. Now, how about less conductive, right? So we're going to put like little isolators here and there. Let's say our bathtub is leaking meaning more conductive. So in a way, now we're going to put little silicon somewhere here and there. In this case, it's going to be silicon dioxide. Of course, we're going to thermally grow and then find a solution to that. Great thing about silicon, and this is a transmission electron microscope image. And when I show this to the students, I mean, I think that's a very powerful image. And even if, after seeing this so many times, I'm still kind of amazed, because it's showing a very drastic, important thing. So this is kind of the interface here. from the silicon to the thermal oxide. How do I know that? Well, silicon can be a crystalline material. So that's why I can clearly see the periodic atoms here located in a certain configuration. Whereas the silicon dioxide, unless it's quartz, going to be an amorphous material. So there's not really going to be a long-range crystal orientation, a periodic orientation. That's why I don't see that kind of periodicity here. That's good. Now I know which one is which. But other than that, I have another thing happening here. A lot of the time when you do deposition, when you do growths, etc., there's always going to be some defects happening. A lot of like cracks, a lot of things might be going on, a lot of dangling things happening. There's still happening in here too, but this interface is really, really smooth here. It's a great thing for silicon, and that's why we have the Silicon Valley. That's why silicon is being used as the most commonly employed semiconductor even, because it grows its own oxide all by itself. You just do the thermodynamically favorable conditions, you just elevate the temperature and bring in some oxygen, and that's it. It grows by itself. So if we want to get some stable electrical insulator, silicon dioxide is here. That's why kind of like when it started with germanium, for example, back in the 1940s, this whole semiconductor industry. So then it quickly switched to silicon because silicon is more abundant. But other than that, silicon grows its own nice insulating layer. Why do we really need to care about the silicon dioxide that much? Because if you look at this figure here, we use silicon dioxide every day in our lives today, because for every little transistor, we'll need some isolation side. We'll need to say, okay, so this electrode and this electrode will not be touching each other. So we need that isolation happening thanks to, say, the gate oxide, which is going to be the most important isolator, the most critical thing ever in a transistor. So this thin little oxide is extremely critical for the safety of our transistors. So transistor, let's remember, is just a switch. We just turn it on and off, let the electrons go from source to drain based on our desire. That's it. And that channel will be formed under the gate, and this gate here, this isolator, is very critical because I don't want this gate voltage to immediately be touching the channel underneath for the electrons. If there's some leakage or if there's some connection between that, transistor is gone, unfortunately. But we have lots of different kinds of oxides existing, so uses of oxide. So if you go to the lab, as a wafer standing all by itself will already grow its native oxide, and that's going to be a very thin oxide, so it's not going to be 200 nanometers. I don't know why I left it like that. Sorry about that. It's going to be like more like 2 nanometers at the best case. Okay, so that's a very, very thin oxide. Nowadays, those transistors, when you look at the cross section again, the gate oxides, these thin gate oxides are very, very thin. You see that that's like 3 atomic layer thick. The gate oxide is only like 0.8 nanometer thick. Why is that the case? Because we're shrinking down the transistors, right, every year. So accordingly, geometrically, everything needs to be shrinking down too, so just like the gate oxide. So the quality of the gate oxide, I will be emphasizing that, is super, super critical. Now, what are the other uses of the oxide? So let's say you put your transistor in here. That's a familiar transistor we just seen, and we have the gate oxide in here. And we could have started with a native oxide in the wafers. It's just like natively grown, like 20 Celsius degrees will already grow some oxide there on the surface of the wafer. How about if we have another transistor here? How are we going to make sure they're not like cross-talking? How are we going to make sure that they are like isolated from each other? Well, this is a little bit of an older technology. What we use like these field oxides to put it like a barrier between the two. We call them the locus in the old days. So that's how they look like, and that looks like a bird beak, as you can see. Literally called as bird beak in the industry. We use more commonly SDI, shallow trench isolation, which is kind of going to be like a planar isolation side rather than these kind of like, this is all oxide. So you see it has like this weird shape. So instead of these kind of field oxide, we switch to SDIs more often. We also use oxide, of course, as a barrier between the electrodes. So I'm going to put a voltage supply here and another voltage supplied from the gate and this location. I don't want them to be electrically touching. So wherever I want to get an insulator, I put the oxide, of course. So this graph is showing you, or these pictures are showing you how these locuses are generated. So in this case, we want to create the silicon dioxide only in this area here, where it's not covered with the silicon nitride. So silicon nitride prevents the silicon dioxide creation. So we have like this kind of a nice opening here. And if we satisfy the conditions, like I will touch in a bit, so we can grow only the silicon dioxide in here. Look, underneath the oxide silicon nitride, a little bit of this kind of connection that's coming from these what we call pad oxides. That's another form of oxide just underneath the silicon dioxide. They kind of connect, and they kind of, because of this growing layer, that gives like this kind of a stress on the silicon nitride that it can withstand. And then once we remove the silicon nitride, we have found our locus layer. That's how it's made out of the volume expansion. We can use silicon dioxide for screening material. Like we've seen in the ion implantation, we're sending the ions from the top, so we can just like use it as a mask and then not allow too much of ion implantation happening here, but it can happen here, or like again more barrier oxides as we start creating more and more of these architecture in the third dimension, and like these kind of very thin, like not super thin, but still thinner pad oxides between each layer. Again, those are common uses, and based on the uses, of course, their thicknesses will be different. Like the field oxides, those are really like, I don't care too much about the thickness that much about them, because they're going to be really, really thick. And then when we come down to the masking oxides, I have to be very careful, say for the ion implantation, for example. And then the pad oxides are thinner, like as you can see. And then when we come down to the gate oxides, yeah, that's like in the nanometer range, couple of nanometers range. So we have to be careful about them. And this is silicon dioxide also has this wonderful speciality, because there's a great way of getting rid of it too. So say you start with silicon dioxide placed on your silicon here. You can dip that into your, not the greatest one, it's a very nasty thing, hydrofluoric acid, HF. If you dip that into HF, well, it will just selectively remove silicon dioxide without touching the silicon underneath. So that's a great way to selectively remove it with what we call the wet edge. So we just not only have a great way of forming a good insulator, but we also have a great way of selectively removing that insulator from the area too. Okay, now looking at this oxide structure, we have a silicon here in the middle, and then around that we have like these oxygens, and making these 4 bonds like you can see. So it forms like this tetrahedral structure, this network. And in a normal silicon dioxide, these networks are binding to each other in this fashion. So we're seeing the connection between the networks. So you see the silicon is in the middle. We have the oxygen surrounding. So if the oxygen is bridging, is being like shared between these 2 tetrahedral structures, like in this case here, or in this case here above, and that's great. That oxygen has a bond between these 2 silicons, so that's a bridging oxide. When we don't have that case here, like in this case, the non-bridging oxide, so it can be because of a defect, or it can be bridging from one oxygen as well, not just to silicon as well. So that's going to be like a dead end, right? So we go nowhere from here. That's going to be a non-bridging oxide, so oxygen. And then the amount of those bridging to non-bridging actually determines the quality of the oxide. You like to increase that as much as possible. Having said that, if all these oxides are bridging, what will we form? We will form a crystal structure like this. If all they're in like nice, smooth condition. By the way, we're looking from the like a planar fashion on a plane here. So it's normally like this, right? Like a tetrahedral in the 3D, if you like to think about it that way. Now we're putting it on a plane. That's why it looks like a triangle. If you can, like, we're just looking at this triangle face here, okay? Anyway, so if we have all these oxygens bridging, then it becomes single crystal quartz, and then it has this density here. But normally, amorphous form of silicon dioxide, that's what we're going to look into today as well. We'll have this density, and it will have this kind of a crystal, which is not like this kind of a nice periodic structure, right? That's why we call it the amorphous material. how do we grow these materials, and what is the mechanism? So we grow them in these kind of furnaces with the heat applied. So we load them into the wafers here. These are all silicon wafers. You must have seen this. This must be familiar from last week's presentation from Terry's CVD, chemical vapor deposition. So in a very similar environment setting, so we have this furnace here. We heat up the furnace. We apply the oxygen, nitrogen, these kind of gas here to do certain intelligent things and then grow our oxide. So these kind of furnaces, when we look at from the side view, they have like these kind of heaters, heat zones, generally like 3, to make the temperature as uniform as possible over the furnace itself. But over the edges, of course, there will be like temperature deviations. Most of the time, if you look, these are wafers, by the way. If you load your wafers like this, so generally I tell my students, forget about the ones towards the edges, because whatever you do, the temperature will not be staying so stable over the edges. So that's going to be like a sacrificial layer, sacrificial wafers. So there are 2 main types of growing these oxides that we're going to there are other ways too, but these are the ones we're going to cover today. The first one is dry oxidation. Well, apparently we're going to introduce oxygen and nitrogen in the dry form from the gas bottles directly into the furnace. The other one, yes, you correctly probably assume that, the wet oxidation. And in this case, we're going to use water vapor to introduce the water vapor form of the oxygen into the furnace. So these reactions will take place. As you can see, we have H2O here, and we have just oxygen in here. And these are kind of like the general the tools and how they look like. Very similar to last week's CVD presentation. We have furnaces in a like the horizontal furnaces or vertical furnaces. But unlike the case with the CVD, where we were favoring some of the time, they're more expensive, the vertical furnaces, but we might be favoring them in CVD. Most of the time, people go with the horizontal ones in the oxidation furnaces, as far as I've seen around me. Okay, so how did we grow this? What's the mechanism? So this is what happens. We start with the gas form of the oxide. That gas, the concentration, drops down by diffusion. So this first one is gas diffusion, and it reaches down to the surface of the growing oxide, silicon dioxide. All the time, there is always going to be, however thick that might be, a little tiny silicon dioxide growing on the surface. And then that's going to be absorbed at the surface. So this second mechanism will be absorption. And then from there on, so we will lose some of the concentration there. You see, like at the surface, we have CS, we have switched to C0 because not all of them will be absorbed. And then that will be going into the material. It's going to diffuse more because the higher concentration is here, lower concentration is here. So that concentration of the oxide, the oxidant that we call, it doesn't have to be oxygen, right? So it could be like hydrogen H2O as well in the case of the wet oxide. That will reach the interface here, the silicon dioxide interface. And so that's the third mechanism, another diffusion. And at the interface, we will have a chemistry taking place, and these chemistries will be taking place. So as a sum of these 4 mechanisms, we can understand what's going on inside the oxidation furnace in an oxide growth mechanism. 1, 2, 3, 4 mechanisms. Again, we have diffusion, we have absorption here, we have another diffusion, and we have chemistry kinetics taking place. So this brilliant young man, I mean, he isn't young anymore, but he was in 1960s. He came up with this this mechanism. He modeled this mechanism when he was like 25 or something, I believe, in 1965. And he published this, and he's one of the co-founders of Fairchild Semiconductor, a very famous company from few years back, decades back, but people are still using his mechanism, his oxide growth mechanism. This is what's going on based on the analytical way of understanding models. So what's going on is this is the thickness of the oxide. It grows very rapidly. We're going to come to that later on. But later on, after some period, okay, some minutes later, it first grows like linearly with time. This is T time. And then it kind of saturates. It's like not linear and parabolically saturating, as you can see. So why is that happening? Why do we have like this kind of a saturation? That's the first question I ask to the students. And some of them really understand it this well, and then they can come up with an answer. Of course, the saturation comes because as we're growing the silicon dioxide, right? So the speed of the growth will decay because even if everything is staying constant, the gas concentration and all the other parameters, we have a thicker silicon dioxide here. And as it's getting thicker, this diffusion process will be more time costly. So it's going to decay the rate of the diffusion, and thereby the reaction rate will be also limited. And then the growth rate will be limited too. That's why it's going to be kind of saturating over the time. So I put this small MATLAB code for you again. With some of my graduate students, we just ran a couple of cases in our oxide furnace that I've shown you. Those pictures were from our lab. And we did try to grow some oxides and then compare that with that gentleman's model. They'll grow. So let's run this. So this is going to ask us first, of course, the temperature of the growth. So I'm going to say like 1,000 degrees, okay? And then this is going to ask me the second thing, what's the crystal orientation of the wafer that you're going to start with? I'm going to come to that a bit later, but let's say 100 for the time being. And what is the initial oxide that we have while we're starting? So let's say we start with 0, okay? Let's see, I hope 0 will make sense. So and then that will give me this kind of a graph. So over the time, so you can modify that if you're familiar. I uploaded this to Canvas too. So it ends around 5 hours, 300 minutes. What we see here is that linear growth, and then I hope you can also see that the kind of like a saturation goes to the saturation. Not really saturated too much, but it's going to saturate soon. So we can try to understand like how much of the oxide we are growing at a certain point. Like say after 20 minutes, we've grown like 15.86 nanometers or so. So that's what we will get after 20 minutes. With a 0 nanometer native oxide. So, okay, so 15 minutes roughly gave us that. So let's keep that in mind. And then let's do this little analysis. Again, doing the same condition, 1,000 degrees, starting with 100. But now I'm going to add like an initial oxide. So let's say we start not with a 0 oxide, but we start with, say, a 20 nanometer oxide, quite a thick of an oxide. So let's see what will happen now. Just calculate it again, so let's compare. So we've seen that after like 22 minutes or so, we've attained 15 nanometers of an oxide. Here, after 15 minutes, or 22 minutes again here, so we are ending up with 33.64 nanometers. But we already had 20 nanometers, right? So comparing the initial case, 20 nanometers, up to 33 nanometers. We've just grown 13 nanometers, right? And without the oxide, initial oxide, we've just grown 15 nanometers. So this is also showing you that without the initial oxide, we grow much more, right? 15 nanometers in this case, 12 nanometers or 13 nanometers in this case. And we're also depleting the silicon while we're starting the oxidation. So we're introducing the oxide from the top, let's say, and we have the silicon material in here. That's the original surface. So I always say this to the students like this. It's like an earthquake. Let's assume that you just like came down into the surface, like you just lost your layer. Why? Because we're consuming the silicon, right? So this reaction is taking place. We're doing this chemistry and we're consuming the silicon. So if this was your original surface, let's try to calculate very quickly how much of the material we're consuming ratio-wise. So let's say we consumed this much of a thickness, TSI. So this is my consumed silicon, right? So this was the original surface. After the oxidation, we end up here. If we multiply that with the density of the silicon, and if we multiply that with the area that we have in here, what area? That's the surface area here, as you can see. That's going to give me the total mass, right? Mass of the silicon that we just consumed. If we divide that by the molecular weight of the silicon, that's going to show me how many moles of silicon that I just used, right? So it's very quickly. That mole, if I use just like say 1 mole of silicon, I'm going to get 1 mole of silicon dioxide. That needs to be satisfied, this ratio. So if I now calculate it for the overall thickness that I just created, the T oxide here that I just showed you, the same area, it's on the same base, and it's going to be multiplied by the same, not the same, the density of the silicon dioxide divided by the molecular weight of silicon dioxide. That's going to show me the same mole, number of moles silicon dioxide will be converted. These two ratios have to be equal. Then if we do the math and try to like get rid of the A's and then divide the things, we will see that it's something like that. If you grow 1 unit length of silicon dioxide, so if this is 1 unit, okay, so you consume like 0.45 or 45% of it, the silicon, okay? So your actual thickness above is like only like 0.55, something like that. Just grown 0.55 units. So I asked this to the students. This might be looking like a very simple question, but it's not actually. So I asked them, let's try to grow oxides for a certain amount of time and just give me like a roughly draw what will be the end result. This is a killer question because they have to consider a couple of things. Look, there's an initial oxide in here, also another initial oxide in here. So the oxide rate will not be the same. So compared to the bare silicon in here. So if we grow like say this much in here, we will grow much less in here. I hope that makes sense. So a lot of the students fail to give this answer here, first of all. And the other thing is, of course, we're consuming the silicon, right? So we're basically going in down in here like this much. How much? Like 0.45% of it. Accordingly, this, since we're growing this much, so this needs to also go down 0.45 of that. So that's going to be like that. And there's, of course, not going to be a discontinuity. So they're going to be continuous. So that's going to be like the general answer after that. But not a lot of them, unfortunately, is able to give the right answer. Okay, coming back to the two different types of oxidation, wet oxidation and dry oxidation. So wet oxidation always gives us a much quicker result. So when we apply H2O, okay, so they're generally done for quicken but still dirty mechanisms to grow oxide. Why? H2O here at the surface is absorbed much more efficiently, okay? So this absorption here is, coefficient is much higher for H2 introduction. So that's gonna grow much quicker for that reason. But the end result is the quality of the oxide, as we will see, is not great. So we will sacrifice the quality, but we will increase the growth rate. So if you like to grow very quickly, but not so great in terms of quality, you can do that. Now, a second thing about that we just quickly talked about it, wafer type, 100111. So these are just these different ways to cut the wafer. So if you have your silicon, like we're seeing in here, okay, we can cut the silicon in many ways, the silicon material, to get our wafer. So we can just get a piece like from this face, right? So that's going to be like, if you just cut it from there, if the silicon is cut in there, that's going to be our 100 material. Or we can cut it like diagonally, right? So that's another way of it. Why not? We can cut it diagonally, get a face like that. That's going to be 111 direction. Anyway, so those are details, but the way that we cut it will bring some different orientations, because the number of the silicons on the surface will be different based on the way we cut. If we cut it like from the face, there will be less amount of silicon atoms on the surface. But if we cut it diagonally, there will be additional silicon atoms that we just cut. What does that mean? They will bring in more possibility of chemistry, more bonds there. That means more chemistry, more quicker, rapid growth. So we will grow the material quicker. So that means 111 will grow quicker. Now let's go back to the little MATLAB code. We remember that we just grew like a 15 nanometer or so. Okay, thank you, Greg. So I'm gonna do the same thing here, enter an oxidation temperature 1000, and I'm gonna do this time 111. And I will start with 0 because I know that it's gonna give me 15 nanometers if I started with 100 type. So if we go here for 22 minutes here, Now you already see the results. Like around the 22-second minute, we grow like 24 nanometers, so it's much faster because we have many more silicon atoms present on the surface, okay? So 111 will grow much faster. How about the temperature? Of course, if we increase the temperature, I hope I have the coefficients for that, but let's see. 100 still, and 0. So I'm doing this not at 1000 degrees, but a much hotter furnace. So that's going to make, if we come down to 22 roughly, yeah, you see that we now quickly grow 96 nanometers. So that was much quicker, from 15 nanometers to 96. We just elevated the temperature. We now know a couple of things. The crystal orientation, how we start with, will also change the rate, but the temperature will also change the rate. And also, we know that the wet or dry oxidation will change the rate too. So this is kind of a recipe that we're just giving to you that what can be followed. We start with a certain temperature, like a slightly lower temperature where we won't have too much of growth, and we ramp it up from that temperature, keep it stable there where we grow the oxide at around 1000 degrees, and then we ramp it down inside the furnace, and then we can take the samples out. During this whole process, we introduce nitrogen and oxygen, and also HCl. So where did that come from? We'll talk about it in a second, but that's also for an intelligent purpose. But nitrogen and oxygen are intelligent. We should put them in there carefully because they have a certain purpose. Oxygen is, of course, for oxidation, but nitrogen is there for stabilization of the surface. It decreases the chances of creating these defect size. More detailed discussion, but it gives us a better quality of an oxide in the end. So another thing to improve the growth rates, as an example, if we dope it, like say here we do an ion implantation, and there we have more, like say phosphorus here and less phosphorus down here. So we have added more ions, phosphor ions here, less phosphor ions. If you do an oxidation on top of this silicon to grow silicon dioxide, this area will be growing much rapidly. The reason is we have destroyed the crystal there much more, so there's lots of bonds dangling. So those will speed up the process of oxidation for us. Okay, what else? So we can create intelligent things out of this oxidation process, like how about a tip, like an electron tip, for example. How do we do this? For example, let's use a mask, and let's try to, like this kind of a mask, and let's try to oxidize this silicon underneath. Well, since we're eating from the silicon itself, we're going to be also consuming the silicon underneath, and then if we apply HF, remember HF, hydrofluoric acid, to remove the oxide, then we can end up with this sharp tip in here. So that's going to give us the nice field emission tip. Yeah, that's the word I was looking for. That can give us the field emission kind of tips. Well, if we also have to cover this with a metal or something like that to convert it into an emitter, but we can have like these kind of tips from the silicon here. Okay, we created our oxide, but how do we measure the thickness of the oxide? A couple of ways. First way is, okay, you have your silicon dioxide, and here underneath you have silicon. How to measure the thickness of it? You can just apply voltage from the top. The voltage, once you apply it, the electrons will try to go through the silicon dioxide, but it's an insulating layer, right? So it won't allow that, but then you apply more and more voltage. So you see that we're increasing the voltage in here in this axis. All of a sudden you break down, that's what we call it, you break down the oxide. That insulator is like so much forced so that you will just like run the current through this, okay? Based on like the voltage where this happens, okay, so you can like understand, okay, so that's the voltage that's corresponding to, so then I have like a correlation. If it's thicker, of course, its breakdown will be larger, right? So for these kind of examinations generally. So you can have an understanding about your silicon dioxide quality, but also about the thickness of your oxide electrically, just by applying voltage. Or you can apply current or voltage again. This is what we call stress analysis, time-dependent dielectric breakdown stress. And based on that stress, the current that you're trying to drive, there's initially almost zero current. Then over the time that you apply like a constant current, not switching to a higher value, etc., there's going to be accumulation of all these electrons trying to tunnel through, right? And then they will just punch through. They will just go to the other side, okay? So that's one other way of doing it. And what kind of a tunneling am I talking about? Now, I also uploaded this to our supplementary materials from also last week's too, but there's this little Colorado's website's little application that you can utilize. This is a quantum tunnel here, a little barrier showing us like how the electron can behave. So let's say we have an electron coming in. The electron is a wave function here. So we see the oxide that's like a barrier in front, and you see that it's kind of like decaying inside, and then just this much of the this many electrons, there's a probability of doing that. Let's also show that reflection. Of course, it's so little that it doesn't even read, but like 2% of the electrons can punch through. So that may not be good enough for the tunneling, but if you make it thinner, or like the oxide is getting thinner, right? So that's the problematic time. So you see, if the oxide is so thin, then we have a chance to tunnel through this oxide. This is what we call the quantum tunneling. And it's one of the deadliest things for our transistors, because the electrons are just going through that. It's not like acting like an insulator anymore, right? And I told you that we need to make the oxides thinner and thinner over the time. We need to shrink down the sizes. Okay, so before going into anything else, there's another way actually to characterize the oxide of the thickness of the oxide. Let's go to NanoHub for that. I gave you the link again for NanoHub. So over NanoHub, please go and get an account. So this is a very useful tool, a great website. And then you can search for MOSCAP here. I gave you the link as well, and you can launch the tool. Over the tool, once you run it, you'll be able to characterize this oxide. What is this oxide? So we'd have a metal, M, oxide, insulator, O, and semiconductor underneath, S. So this is why it's called MOSCAP. It's a metal oxide semiconductor capacitance. We have a thickness of 0.1. We know the thickness here, 100 nanometers. And then we know the dielectric here. It's a constant, dielectric constant. Think about it like refractive index, dielectric constant. It's given as 3.9, okay? And let's run this case. You can just put your electrodes and try to measure the capacitance that you get out of it, okay? So the CV characteristics, by applying different voltages, you can measure different capacitances. So here I see that it's shown in the form of nanofarads, 30 nanofarads or so, as we're increasing the voltage here. The voltage that we apply from here, that's connected to ground. So we are applying like minus 3 volts and switching from minus 3 to 4 volts or so. The details are not so important, but just to give you an idea like how to characterize this is a great way of doing it with CV measurements, what we call the capacitance voltage measurements. So instead of like this, let's say if we had like 50 nanometers, what would we get? If we rerun this again and get the results here. Okay, so we will get a different CV response, a capacitance response. That will be corresponding to a different thickness of this insulator here. How can I look at the two cases? Okay, so I made this thickness to be smaller, and the gate insulator thickness is smaller, then the capacitance value, as you can see, improved. So now we're at 60 nanofarad instead of 30 nanofarad here. Why? Because this capacitance is related to the thickness, inversely related to the thickness of this oxide. What else can I change? I can also change this to be higher, for example. Let's make it like, say, 2 times 7.8 or so. I can use not silicon dioxide, but another oxide, which will give me a dielectric constant differently, like 7.8 instead of the 3.9. And we will get a different response. So not just we can determine the thickness of the oxides. Now it's in the general sense oxides, but we can also understand what oxide we're looking at as well. So now this gave me a different response. So I will say CV characteristics. So you see, now this is even higher, right? Yeah, higher. It's like 100 nanofarads all of a sudden, because, and that's also very expected, because we changed this oxide, silicon dioxide, which had a lower dielectric constant with a higher dielectric constant. We call these oxides high K, and I gave you some papers to read about if you're interested. But just to compare the results, this is the previous result, and now we get a higher capacitance out of this, thanks to the fact that we just employed a different, not silicon dioxide, but a different oxide, and we'll come to the application of that. But having said that, and that's what Rich will also show us, we always kind of use more or less the optical ways. And one of the famous ways is just by using your eyes. Your eyes are actually nanocharacterization tools themselves. So our eyes can see a difference of 10 nanometer in terms of thickness. So if you have grown a 10 nanometer of an oxide, when you look at it from the top, that thickness will be seen by our eyes because the the reflection properties will be different, and we will have a different response, a color different response from the surface. So our eyes are really can tell that much of a difference. But how about say a 1 angstrom of a difference? So that's the precision now we're looking into. There we will use an ellipsometer, a dedicated tool where we will locate the wafer, send our laser from one side, we'll look into that a little bit more in depth, and then get the laser reflection on the other end, on the other branch, and collect the information from our surface. This will tell us how much of the thickness we have just by looking at the laser's reflection from the surface. We have a chart to guess the initial thickness by looking at the different colors that we can have from the oxides. But these are the ellipsometer measurements that I got from our lab. And you can see that, for example, this is the native oxide that I was referring to. We have I go to the lab and this is my silicon wafer. I get some measurements and I say that this is 1.4. Towards the edges, we have a little bit of a thicker nanometer in terms of nanometers. And in the middle, I have 1.1 nanometer of a native oxide. This is the thickness. After a growth of 7 minutes on that silicon wafer, I obtain a different measurement. Here you see that we've grown a 14 point something. It's not identical, right? So it's not uniform all around, but kind of consistent as well. Within +1, -1 nanometer, we have grown a thin film of an oxide, around 14 nanometer after 7 minutes. So I get the results like this by scanning the surface like that, getting the ellipsometer measurements from different points automatically and then portraying on the graph. But having said that, this 7 nanometers, if you think about it, is very rapid. And I've just grown 15 nanometers already here. What was the result? Remember, what was the result for us to get 15 nanometers on a 100 surface? We just done that in MATLAB. We've seen that was 22 minutes, right? So this rapid growth of the oxide is a bottleneck, or a headache for us because it's happening so fast. And as you can see here, based on the 1965 paper from Dale Grove, the famous gentleman that I showed you earlier, you see that these are the experimental results. And the curve that's corresponding to that temperature is only this. So you see, we're expecting analytically like this. And because of its rapid growth of the oxide, we're really far off. It corresponds to as if we just altered the temperature of the growth, increase it to 1100. So there are other papers that came out later in the following years that can predict this growth a little bit better. Like you guys can see here, it's kind of sticking to this kind of growth a bit better. But when we grow to grow at lower temperatures, there's still a different issue there. So Masood is one of the other famous person who worked on this. So they've come up with different models, but still there are discrepancies, having said that. Now, if you remember, we introduced hydrochloric acid, HCl. Why was that? The reason is we have these kind of non-idealities. These are a little bit more detailed discussions, but potassium, sodium, these kind of things can easily come from the surrounding environment even inside the clean room. So, and they will kill your transistor. In order to neutralize them, you add this very reactive Cl, right? So you just go through this reaction, and that will capture the sodium, for example, to create the salt. So to immobilize those mobile ions that you can introduce from the surrounding, you introduce HCl. And there are other defects that can happen and then can change the performance of your oxide. Well, a couple of things that can happen is like those dangling bonds on the surface. So there might be like some silicon, or you can see here some hydroxyl groups that are not really nicely grown. So this like a dangling bond here that's not oxidized here, okay? There can be some broken bonds in here. So this silicon is not sticking to the oxygen. So that's a broken bond, a fixed charge here, trapped charge here. So this one is bound, so this is why it's called the fixed charge. These are not bound, so they're like mobile ions, so sodium, potassium, that's why it's called the mobile charge. And they will slowly destroy your transistor. All these things that are happening can destroy your transistor. So people kind of switch to what I also showed you, high K dielectric materials like hafnium dioxide. Then they use ALD, atomic layer deposition for that. And this actually lowers down the leakage current a lot. The leakage current, again, remember, is the current coming from the gate into the material here because we're shrinking down the thickness to, like, say, 1.2 nanometers. While we're shrinking down the D thickness here, that is dropping down here, right? We're getting actually an elevated, as you can see, capacitance during the shrinkage. Well, if we kind of like go over this problem by introducing another dielectric here, like we're introducing now epsilon, higher epsilons here. So we're going to introduce another epsilon here. So as you can see, we just replaced that with hafnium dioxide, for example, that has a higher epsilon. But in order to give us the same capacitance from this capacitance, meaning that the same kind of insulation mechanism in a way, we can work with a larger D, not a 1.2 nanometers. You can see that it can be like corresponding to a 3 nanometers. So we can work with a thicker dielectric now, which will be a better isolator for our structure. So this will have a similar capacitance response. And while we're still having like fast transistors as before, we can have cooler chips with less gate leakage, with less power consumption, which will be a great thing to end up with in the end. Right, so the last talk, and then I will leave the floor to Rich, I can say 10 minutes or so to wrap it up. I will talk about AL, the atomic layer deposition. So it's similar to CVD. There's lots of text here, but I'm going to quickly go over the essential points here. It's kind of very similar to CVD, but in different than CVD, we have like precursors, precursor 1, precursor 2. We'll introduce these two different types of gas into our furnace, okay? So that's how we will grow this material in the atomic layer deposition fashion. But different than the CVD, we'll introduce them one by one. So if you're introducing precursor 1, we need to make sure that this valve is closed and we're not introducing precursor 2 at the same time. So that's one important thing. It will be a self-limiting surface reaction. So we will introduce the chemistry and then I will show you more in depth, but the chemistry will drive a lot of other things in here. But then even though we introduce more from, say, precursor 1, there won't be any surface to react with. So that's why we call it self-limiting surface reaction. I'll talk about it more, so that we're going to be more clear. So we have like a balance between the chemistry and desorption, saturation, absorption and desorption. So the chemistry can come down, the precursor can come down and can be desorbed to outside or can go into the reaction here. By the way, these are generally much lower temperature deposition techniques, ALD, so it's an advantage compared to CVD. But it's a growth that's happening layer by layer, atomic layer. So that's why it's given this name, one atom at a time. So that's the rate that we go with. I have a better slide than this, but just to give you an idea, if we'd like to grow A plus B on our surface, we will grow A's and then B's and A's and then B's. So that's the fashion that we're going to grow it with. So still a lot of things will be dark for you. If you're not familiar, that's all okay. I'll come with the better slide that I was referring to. But like I was saying, there is going to be a cycle. We'll start with the substrate and then we're going to introduce our first reactant, our first precursor, and then we're gonna pump that out, the ones that are not consumed. So you see, we're like limiting the surface. The surface is all gone into reaction. So there's nothing that's not going into reaction. So that surface is kind of saturated. Then later on, we introduce the second precursor, and that goes into the reaction. So you see, we have the surface reacted, and we then pump out the second precursor, and that's the cycle. One at a time, we just like repeatedly introduce one and then the other, one and then the other. One monolayer can grow like, if it's like 1 angstrom at a time, if we grow just like 1 angstrom out of one cycle meaning introducing A and then B, for example, after 8 cycles, okay, we will have achieved 8 angstroms. So that's the beauty of the ALD. If you have how many cycles that you have grown, then you will have like a super precise idea about the thickness that you have grown. There's no way to be misguided about it. Now, we're going to do alumina together with Rich here today, so I will specifically concentrate on that. So how do we grow alumina on a silicon substrate? So let's say our silicon is here, and I told you native oxide, right? So we will immediately have like these oxides, oxygen coming down onto the surface, and they kind of form these initial hydroxyl groups on the surface, which is just a combination of O and H tied up to a silicon dangling bond and unsatisfied bond. It just satisfies its bond by binding it to the oxygen and then the hydrogen. Then we flow in our first precursor. Our first precursor will be like Rich will show us TMA, trimetal aluminum. It's just made out of CH3s and then 1 aluminum in the center. That's it. So when it comes into the reaction, this reaction will be run. And this will be run, thankfully, because we will introduce the precursor, but also we will elevate the temperature. Like Rich will elevate it to 300 Celsius or so. Then oxygen will go and look at the oxygen. It used to have this hydrogen, right? But what do I have here? CH3, right? So CH3 will love to get that one dangling hydrogen from the surface to create the stable CH4, the methane gas, right? So that methane gas will be formed, and then the hydrogen will be gone, and then the aluminum will be tied up to the oxygen on the surface. Then what do we do? Well, we just continue sending the TMA. But over the time, we will have this chemistry fully covering the surface. So everywhere will be covered. By the way, it's not a line of sight of kind of deposition. So everywhere inside our chamber will be covered by the TMA. Then what will happen? Well, these will be will have no home to react with these new TMAs, not these. These are the CH4 that's just created, but the new incoming TMA will not be able to land anywhere because there's no opening. So we'll just suck out those excessive TMAs and then wait and then send the hydrogen. So repeating, we've just sent our first precursor that went into this reaction and formed CH4, and then we continue sending TMA, but there's nowhere to react with, so they will all be sucked out. So that's the pump down. And then we'll send our second precursor, hydrogen, water basically. What will happen? Well, again, the CH3s are here, right, on the surface, now on the other branches of the aluminum. So those will get the hydrogen from the water, and then again, CH4 will be created, like you can see here. Again, CH4s will be created, and then the oxygen will be bound to this aluminum. Great, so I started with oxygen. I just formed my aluminum. Now I just formed my oxygen layer again. So as soon as this is ending, we go back to where we started with. Remember this? We have hydrogen here, we have oxygen at the bottom. So that's what we started with, and that's what we end up with in the end after one cycle. So this is one cycle here, and if we do like a couple of cycles, we will grow that many. So we just done 1, 2, 3 cycles, and we just achieved this many on the surface. So you see now how controllable this is, right? And how conformal this can be. What I mean is the uniformity is absolute. Everywhere is now 3 aluminum. That's wonderful. So we have the TMA pulse that Rich will show us. there's going to be a pulse on the screen. That's going to be followed by a pump down time where we will suck out the excessive amount. By the way, these pulses, they don't look like pulses, right? What can this be, this delay or this tail? That's the methane gas. We will form the methane. That means that your reaction is taking place. So that's a great sign. If you have like not a short pulse, but like these kind of tails, that means the reaction is taking place. So you have methane gas occurring, you're sucking that out, and then you pulse the other precursor, water precursor. So layer by layer, we will grow the aluminum oxide. It's a gentle deposition process, doesn't entail too many high temperatures. It's a lower temperature compared to CVD, and it's not like PVD, like we discussed sputtering, right? We were bombarding the targets, and then there was plasma. Plasma could attack the surface. All those things could happen, so that's why it's really much gentler. It's a stepwise process, so it's can be slower than the other processes, so that's the drawback. But we really know the continuous film. We know where we are. We know how many cycles we have counted, and then we will know what we will end up with. So it's going to be really giving us a great conformality. This is what I mean by conformal coating. You see the thickness here on the sidewall will be identical and everywhere. So on the flat surface and on the sidewalls, we will have the nice layer deposited on this conformal coating. So it can really conform over the surfaces. So these kind of funny surfaces can be nicely patterned surfaces can be covered. What else can we do? We can grow the same hafnium dioxide over like say 2,000 wafers, and we will get the same kind of thickness over and over. So this is a very repeatable process. And if you get like say an ellipsometer measurements on a wafer, you see the quality, like it's not really changing too much. It's great. It's all over around the same numbers. So great control, great uniformity, great conformality, all bring us into this. And then we will analyze with Rich here, we will put that under an ellipsometer. We will have an initial oxide though. So let's start and let's do this simple experiment together in the virtual experiment case. So we will start with a wafer. So this is what already Rich has done. So he put that into an ellipsometer, first a silicon wafer probably, and looking at the silicon wafer under an ellipsometer by looking at the reflection properties, so we can try to understand what we're looking at. So like any material, silicon has its refractive indices. Those refractive indices can be real and imaginary. If you're not familiar with this concept, don't worry. It's just a complex number. It doesn't have to be like refractive index is 1, like for air, right? It can have an imaginary component too, over the wavelength spectrum, so that's it. And looking at the reflection properties, let me bring the MATLAB again. Ellipsometer 1, this is the first one that we will run. So it's going to ask us like, what is the angle that we're coming in? So we generally, ellipsometers are run at like 50 or 70 degrees, let's say 50 degrees. And then, as you can see, the ellipsometer can really like extract the refractive index of the substrate we're looking at. Now here we're looking at two things. The data that I gathered for the silicon wafer, that's the original silicon wafer, and that's the data that I will collect based on the reflection and on the photodetector side. So this is again the refractive index, imaginary and the real components. How does it know that? Well, you have laser coming in and just reflect from the surface. You have a photodetector here. Just by looking at the reflection properties, we can try to decipher what we're looking at. And we can pinpoint the material we're looking at, like it can say, oh, I'm looking at silicon. Now, continuing, we have grown a silicon dioxide. And this is what I do with the students. Go to the second code and try to extract the reflection properties. The photodetector here will have two properties. They don't have to know the details. It's just like psi and delta, these two properties, okay, at two different reflection angles. The student can come at 50 degrees or 70 degrees. Based on that, they will get different psi and delta. That's just what the photodetector will get, those two parameters. From that, it will have like a lookup table and can decipher like how much of a native oxide we had initially. So for this, let's go to ellipsometer 2. So the student will do this. So ellipsometer 2 run. Now the student will have to guess the thickness. I know the thickness. I know that it is 810 nanometer or so. So like around 70 degrees of angle. And then it will say, what is the wavelength that you're interested in? 632, the usual helium neon laser. And it says me, for that, you will have a psi of this and a delta of this. So these are the expected values. So what I want the students to do, I hope you can imagine, I don't give them the initial thickness of the silicon dioxide. I want them to find it for me, work as an ellipsometer. And just by a couple of runs, they will be able to figure out these psi and delta numbers, okay? So they will try to see if they are close to what we start with. And then there are other more complicated things. I don't want to take your time or Rich's time too, but you can grow aluminum oxide like we will do today. And you can also try to understand the psi and delta as well, and then determine the thickness of the aluminum oxide as well. So this is an aluminum oxide that I grew here at Penn State, and you can look at the precision. We just tried to grow 10 nanometers, and look at the numbers here, 10 nanometer, 10.4. It's very, very precise, okay? And then another from another wafer. So that's super repeatable and super conformal, super uniform. Now here we just grew like over 6 nanometer of silicon dioxide. We have tried to attain a 9 nanometer of aluminum oxide. So this is the initial 1 nanometer, 1 minute thermal oxidation, 6 nanometers, supposedly 6 nanometer, but look at it. It's like in the range of 5 to 7, right? It's not uniform. So this is the bad thing about the thermal oxidation. It's not uniform at all. And how about the other one here? We have a much uniform case here because when I just concentrate on the aluminum oxide that I grew with ALD, not with thermal oxidation anymore, I have like 10.8 to 9.8. So like 1 nanometer range, even less than that, plus minus 0.5 nanometer, that's a great range to work with. All right, so I just wanted to emphasize the great precision of ALD and the great prospects that it can bring. Now I'm gonna leave the floor to Rich. So this is their ALD, Kurt J. Lesker, right, Rich?
Correct. Correct.
What was it, 150 LE?
Yep, this is a ALD 150 LE.
That's a great tool. That's the same tool that we have here at Penn State.
So I'm just going to show like these couple of screens we have, and then we'll get to the process, and then we'll move on. All right, so this is the vacuum window. So this shows me that the vacuum is operating. One tour is where we do our process at. I've got the process kind of already started. I just have it paused, so it's been stable here for a bit. This is my deposition screen. I can look at this and it can show me the valves, and it can show me that I have my argon flowing, and it can show me that I have the TMA and things like that in my favor here. Here's the heating screen. This can show that if I'm heating, how well things are. I can keep an eye on different heating elements and how things are. And then we have our process screen. So this is the screen we'll be looking at as things go down and start happening. So once I go down here at the bottom of the screen, I have to open up our recipe monitor, and I will click resume. So it will finish counting down. And then once it gets to 0, it will finish starting the process. If you look at the screen right here in the middle, it's my cycles in the cycle counter. So you can see that I had run 10 cycles already today. I did that kind of as a warm up. Now I have a wafer in there that I measured this morning. I have approximately, I was getting a few ranges between like 6.5 to 7.5 angstroms of the native oxide on my wafer. We're going to try running 15 cycles and see what our results are on the ellipsometer. So this won't take very long as it continues to go through the process now. Now it has started. You can see on the screen. I'm going to change it and tell it we want to do 15. And it will start introducing our TMA and our H2O in the cycles, as Ozgur mentioned, with a little bit of time in between each one to take away the unused material. if I go, let's see. Okay, well, it tells us right here. So here's our doses, and then we got our purge time. I believe it's all in milliseconds. So we're at dose 2. So it does kind of go by a little bit slower than you expect. Let's see what's happening in the deposition screen. We got some things changing in here for us. Not too much. We're maintaining pressure. We're maintaining temperature. We got our flow of 60 SCCMs of argon. So we're doing well. Heating is maintaining pretty well. I don't see things fluctuating a whole lot. So we're in business. And as the graph and the cycles go, you can see it automatically kind of adjusts itself as it gets situated with our cycles and our process here. The red line is our counter that you see on the screen. So let's see, this ALD machine we purchased from Kurt Lesker. Ours is pretty basic. Ours only takes 2 ampules. We just have the TMA, we have the water, but you can get them so that you can put several different materials in the machine, and then you can have it programmed and write your recipes. It'll open up the necessary valves and all kinds of stuff you can do. Ours is just a simple one. We just use it for teaching. We use it to show the students that you can make things pretty accurately once you understand your tool. I don't know if this has come along to be very popular in the production of semiconductors and such yet. Last time I was talking with somebody, I know that was in the works, because it's not exactly what you call a very fast process. As you can see here, we're doing a cycle every, I don't know, 15 seconds, 20 seconds, maybe something like that. And we're halfway done with all of my talking here. Let me see what else I have up here I can show you guys. So up here at the very top, it's got a little record of things of what happened, and we can go back through that and we can research anything that may have been gone wrong, or if the system stopped, it will change colors. It'll show us an alarm up there, things like that. If the door was accidentally open, it will give us an alarm. So that's a place where we can look for all that information. What is this? Oh, we use it for research. So yeah, so that's our tool. And we're getting close to being done here. Yeah, we're at 10. We do have this other window. I believe this is, we could use this to monitor our system. This system will record everything. It will record the steps, it'll record what we ran, how long we ran it, all the errors. So we could always go back and check something out, or we could also work with Kurt Lesker, and they can help tell us when it went wrong. Here's the recipe window. I'll pop that up there. I think if you guys can see it, I hope you can, because I shared the desktop. So this is all we have set up for our machine. Like I said, ours is pretty simple. We just got it for teaching purposes. So we just do the one thing here, the ALD, the AL203, so the TMA and H2O. We have other things in here. We have a maintenance section, so we can run maintenance for our ampule when we change it. We have the PC pump, which is what I ran in the beginning. And I also did the ALD heating. It's at the top, so that turned all our heaters on, set them the temperatures for our process. Now we could vent our system, which is what we'll do next as soon as it finishes, which is going to be soon now. We also, when they were here, we made this thing called layup. So this is so we can just turn our system, basically turn it off. Since we are not a high usage facility, we're not open 24/7. This gives us the opportunity to let the instrument take a rest. Then there's a few other things in here. And we are in the last cycle, so we are almost done. Then I will do a PC vent when it's ready. So now it's counting down. So I go to the monitor, it's not here no more, okay. So now we have this countdown, I guess, resting period while things do what it does and we're continue to evacuate things from our chamber. I'll probably just shortchange this a little bit so we can get it out and measure it. We're not doing anything super critical. We're just trying to get you guys a good visual here of what's going on and what to see. So let's skip that. Let it finish. All right, so it's closing out the recipe, setting itself up so we can continue to the next one. We got our green here telling us our recipe is finished. Close that. I will go over here and hit PC vent. It's going to ask me if I want to do it, and I'll just say resume so that yes, we want to do it. So this takes a few seconds, a minute or so maybe, probably less, to vent our system out so we can access our wafer. And then once this happens, I can release the floor back to Ozgur real quick to say whatever you would like while I get out the wafer and take it over to the ellipsometer, and then I'll pop back on with that tool. Okay, skip that. All right, we're almost to the end of this. So we're just going to measure with the ellipsometer. We're going to just measure just the same recipe that I used at the beginning here. It'll be good enough for us, I believe, here. So we got the green, we're ready, we're closed, we're vented.
This from my friend, good friend Bangzi, who's an engineer at our material research lab, nanofabrication facility. So this is the tool that Rich worked on today, Kurt Lesker Thermal 150 LE. So it's a great tool, by the way. So people are really extensively using it, and it's a multi-user facility, so it's really hard to find it alone as well. But we have other ALD tools, and some tools also have a plasma concept also incorporated into this too. So they use plasma together with the ALD to speed up even the process. Like Rich was showing, this process might be a bit slow. In the end, these are the growth rates out of cycles that we have here. Like Rich has done it at a little bit of an elevated temperature, higher than 300, so it was like 330. But the one cycle is expected to grow like 0.84 angstroms or so. So he's done it for 15 cycles, but at a little bit elevated temperature, 330. What will happen if everything was the same? Then you can just multiply and find out the expected thickness at the end of the ellipsometer measurement. But just to give you a little bit more idea, these are the curves for temperature dependency. So this x-axis is temperature, and this is the growth rate per cycle. So you can see that there's a sweet spot, like around 200 Celsius or so, we can grow the aluminum highest efficiency, because that's the location where the chemistry versus desorption kind of like saturates the chemistry, wins over the desorption. What's the desorption? Well, if we heat up the surface a lot, like Rich has done, like over 300 degrees, we're losing the growth cycle, the growth rate, because the particle is heated up, so it can get loose and then get released, and so your deposition rate might be dropping down. So 200 Celsius is kind of the highest deposition rate, but you can also run it like Rich did at higher temperatures to make sure that, for example, at even more controlled growth rates, even slower but more controlled growth rates can be achieved. So having said that, I will stop sharing and.
All right. It looks like I'm sharing the screen. It's kind of nice using two computers here. All right, hope you can hear me. And so what I'm going to do is I put our wafer on our stage of our ellipsometer here. I have our laser window open so I can check for adjustments here. So I'm going to make an adjustment. I want to get my little crosshair there in the center. So this should be a quick adjustment just because I've been adjusting already today. So there we are. We just got to be right in there. Works. That's a good sweet spot. Now I have this alignment laser that shines down. You can see when I block it, it moves away. So I want to block it because it interferes with certain measurements. So I'm happy with that. And I say, okay, so I've got my stuff entered in here. I've got, I know I'm going to be pretty small and thin. So I have 100 angstroms in there as my expected thickness. So the instrument knows about what it's going to see. I have a few numbers in here that I get from a chart that I use that comes with the instrument, but you also get these numbers online.
Rich, can you show them the psi and the delta over there that I mentioned down at the bottom?
Down here?
Yes.
Here we go, right there. There's our psi and our delta. If you want to say something about that, Ozgur, be my guest if you know what you want to.
Oh no, I just mentioned that in the MATLAB, the virtual lab that I prepared for them. Those are the things that the photodetector will get. So that's how it kind of predicts the total thickness that we have. Great.
Okay, cool. All right, so I've aligned up my stage. I've got my power. So basically what I was doing there is that my light laser coming from the side at the angle, this is a fixed, I believe it's 70 degrees. It's deflecting, refracting, refracting, whatever here off of our sample and to the other side where we have our sensor. So I was making sure I had that alignment ready to go. And then for our instrument, all I have to do is click on this measure and calculate button. It's going to give us an estimate. And we got 6.8. It's right here. I hope you guys can see it. 16.8. So I started out with about 6.5, maybe up to 7, and measuring it a few times. So it looks like we achieved kind of the goal that I experimented with the other day, was to put down the top about 10 more angstroms on top of that. And I did. So
it's very repeatable, right, Rich?
Yep. It was virtually the same. You know, I started out a little bit thicker oxide layer, but I went from like about 7 point something to then after I ran 15 cycles, I put it back on. I had about 17 to 18 was my numbers. So yeah, it was very repeatable once I knew what number of cycles that I wanted.
Great. Yeah. So that's about it. Great demonstration. I hope you guys enjoyed today's presentations, and it's almost 2 o'clock, 2:01. So next week will be great. Thank you very much, Rich. So next week will be about confocal microscopy. So thank you, everyone.